All right, so we just finished talking about London dispersion forces. This video is going to go over the dipole-dipole interactions. Now, the London dispersion forces are the only intermolecular forces that we would find between nonpolar molecules. But the dipole-dipole forces are what we're going to find between polar molecules. Because as we know, when we're drawing polar bonds, we would put these dipoles, these slightly negative and slightly positive signs on the ends of our bonds to indicate that the electrons were shared unequally and to indicate that one end, the sulfur here in the middle, was slightly or partially negative, and the hydrogen here in the middle was partially positive. And that's just indicating which one is hogging the electrons a little bit more. Now, the dipole-dipole interactions are going to be a little bit stronger of an intermolecular force than we saw with the London dispersion forces because these have permanent dipoles. The London dispersion forces were just temporary, just based simply on the movement of the electrons as they naturally move and interact around the nucleus of the atom or the molecule. But these have permanent dipoles because of the electrons being shared unequally between those atoms in that bond. So those permanent dipoles create this stronger attraction between, for example, the hydrogen of this one molecule and the sulfur of this other molecule. So the larger the dipole, the stronger the attraction we're going to have. And we can tell that based on the electronegativity differences between the atoms in that bond. So let's take a look. So we want to know which of these would experience dipole-dipole interactions between like molecules. Now, I am going to highly recommend that if it's a covalent molecule, that you draw it to see if it's going to be a polar or a nonpolar bond. Unless you can tell just by looking at it, you really should be drawing these things so that you can see is it polar or nonpolar, so you can answer these questions correctly. That's one of the problems with this intermolecular forces concept is that you kind of have to go through different layers of thinking before you can actually answer a specific question. So carbon dioxide looks like this. It's a nonpolar molecule, so it would not have dipole-dipole interactions. We would have to have a polar molecule. PF3 would look like this. And of course, there's going to be dots on my fluorine. And then phosphorus would also get dots. So yes, PF3 would have dipole-dipole interactions because we've got the lone pair on our central atom. My fluorine is more electronegative than the phosphorus. So we would have those permanent dipoles and those would attract between other nearby molecules of PF3. SO3, we've already drawn this one. So let me pop this up really quick. SO3 would look like this, whoops. And is this a polar molecule or is this a nonpolar molecule? It's nonpolar, so would you expect this to have dipole-dipole interactions? No. Now here's a trick. For letter D, I don't have to draw that. I can tell just by looking at CH3Cl that my carbon is going to be in the middle. I've got 3 hydrogens attached to it and 1 chlorine. That automatically means that it's going to be a polar molecule because there's going to be different ends. I don't have to draw that to see that. So I know that that is going to have dipole-dipole interactions. So let's look at this next question. Which of these would experience dipole-dipole interactions between like molecules? So same thing, we need to draw it. With letter A, you might think to yourself, well, I don't have to draw this. I know it's going to be linear, but do you? Do you know that there's not any lone pairs on that central atom? If you don't know, you might want to draw just to make sure. And if you draw, you would look like this. And yes, that's a polar molecule because we have different ends. One's hydrogen, one's nitrogen. So this would have dipole-dipole interactions. Do I have to draw letter B? I don't have to draw letter B. I can see carbon's in the middle. It's got 2 hydrogens, 2 chlorines. That's going to be 2 different things. So that would have dipole-dipole interactions. SO2 is going to look like this. Whoops, forgot my bond there. So SO2 looks like this. I can see that this lone pair of electrons is going to make it a polar molecule. I know that we're going to have our dipoles. And so I know this would experience dipole-dipole interactions. Letter D, do you have to draw it? You should, because you don't know if this is going to be bent or if it's going to be linear. Is it going to have lone pairs or isn't it going to have lone pairs? So why don't you try this out? You draw SiO2, or sorry, SiS2 to see, is this polar or isn't this polar? Will it have dipole-dipole interactions or won't it? Let's see what you guys say. And let me know if you guys have any questions about dipole-dipole interactions.